Hello. Right now we will work on some questions from section 13.1. It's on space curve, vector functions and space curve. Now I will do some problems from these sections. I hope you can enjoy and learn from this. I start with number 2. Just wait. Number 2. Find the domain of the vector function RT. That's t minus 2 over t plus 2 sine t, and then ln of natural log of 9 minus t squared. Okay, for the x component, the domain will be the domain for xt will be is all real numbers except t equals to negative 2, huh? Except t negative 2. So everything's okay except negative 2. For the y component, the domain is, oh, that's a sine function. So it's continuous everywhere. Therefore, the domain will be all numbers also. And then for the z component, the domain will be all t where natural log. So the argument of natural log has to be strictly positive, right? So let's solve that one. So first one, the critical numbers, where I set 9 minus t squared equals to 0, we will get t plus minus 3, right? And then second, we do the sine graph. We learned this in Calc 1, by the way, and supposed to be in pre-calculus when we solve polynomial inequality. Negative 3, and then 3, that's 0 here, positive, negative, negative, and we need the positive part. So the domain here will be between negative 3 to 3, right? Now, so the domain of vector function RT will be the intersection for all of those, which if you think about it, let's sketch that first. Okay, so for ft is everything except negative 2. Okay, for gt everything's okay, and then for ht between negative 3 to 3. So we are okay with this interval here, right? When we put things together, okay, so we can say that the domain is from negative 3 to negative 2 union negative 2 to 3. Okay. That's for number 2. Let's see number 4. Find the limit. The limit of that is, let's see the x component. That's limit t goes to 1 of t squared minus t over t minus 1. That is equal to, let me do it downward. That's equal to limit t minus going to 1. I factor t, and t minus 1 cancels, and so this is 1. Now, I assume you know how to write limits notation properly. Okay, there are times, let me at least emphasize a little bit. Okay, there are times you look at the question, you know the answer right away, but still you are required to write properly. Okay, I know some of you think like, oh, you know what, t minus 1 cancel, so I will have the t only, and then I plug in 1, so you say 1 right away from there. But this expression basically means you are putting 1 into in place of the t's and say this is equals to 1, which is not true because you end up with 0 over 0. That's not what you are trying to say, right? You are trying to say that limit of the numerator divided by the denominator. What happened is the t minus 1 cancel first, right? Okay. Why we are allowed to cancel that t minus 1? Because of the condition of limit. T is very close to 1, but not 1 yet. Therefore, we are allowed to do this, to cancel this, right? Okay. If t equals to 1, this is not true. Okay. Maybe I write it this way, the proper mindset. T minus 1 over t minus 1 equals to 1 for t not equals to 1. It's undefined for t equals to 1. Okay. So we need to do it in 2 steps. First, t minus 1 cancels because t is not 1 yet, right? That's why we get from here to here. And then after that, we replace the t by 1. Okay. Now, saying that this is equal to 1, you are saying that you replace the t by 1. That's what you are saying. Yeah. I know that's not what you meant, but that's what it means. Okay, if you say it that way, that's what it means. So instead of just saying, oh, it's equals to 1, Thomas, I look at that, I know the answer. Trust me too. But you are still responsible to show your work as precise as a Calculus 3 students. Okay. So you are saying that, hey, you know what? It's the limit condition, t is approaching 1, which means t is not 1 yet. That enables us to cancel t minus 1. And then after that, I plug t equals to 1. So you see, first t, you are saying that t approaching 1, which implies t is not equals to 1. That enables you to cancel, right? And then in the next step, you replace t by 1. Okay, you cannot make this into one sentence. Okay, you cannot make this into one sentence. Yes. I know you may think that, Thomas, you know what I meant, but still, I cannot judge you from what I think you try to say. I have to judge you from what you actually say. Okay. And trust me, our scientific community actually hold that standard. Say what you mean what you say. Okay. The y component, I think this one is easy. Limit t goes to 1 for square root of t plus 8. Oh, that's continuous there. It's continuous at 1, so this is square root of 1 plus 8. Square root of 9, that's 3. And then for the z component, limit t goes to 1 of sine pi t over natural log of t. The thing is, when I plug that t equals to 1, we will get sine pi over natural log of 1, which is 0 over 0 case, right? Okay. So what we will do? I think we will do L'Hopital rule, right? L'Hopital rule, limit t goes to 1 of the derivative of sine pi t will be pi cosine pi t over the derivative of natural log of t respect to t is 1 over t. Okay, then when I plug in t equals to 1, I will get pi cosine pi, which is 0 over 1. it's 0. Okay, so the limit as t goes to 1 of that vector function, let me write it in vector notation right away, of t squared minus t over t minus 1, and then square root of t plus 8, and then sine pi t over natural log of t is equal to 130. Okay, let's go on. Number 15 and 16. I didn't really mention this in my lecture, but I want to go over this to show you another way. So there are actually plenty of ways to imagine a vector function in 3 dimensions. Okay, now one of the technique is to do projections of the curve on 3 coordinate planes. So let me do, for example, number 16 first. If I have more time, then I will do number 15. Okay, number 16. Okay, we have RT equals to that, right? Now, when we say we do projection on the 3 coordinates planes, it's basically as following. Okay, we have XY plane and XZ plane and YZ plane, right? Now, so if you have a curve in 3 dimensions, let's say that curves looks like this. Now, then you want to see first, for example, what is the projection of this curve on the ground? For example, it looks like this. On the ground. Okay, can you imagine that? Okay, now this part here is the projection of the curve on XY plane. Now, then how do we do that? We basically pick, on XY plane, we basically pick the X and the Y component of that vector function only. So that's t comma t, right? The X component and the Y component only. Okay, but when you have that, this basically implies we are looking at X equals to Y, right? So on XY plane, it is actually a diagonal line with slope 1, right? Okay, now next, how about on YC plane? YC plane, the right wall, YC plane, we have t and t squared. Okay, so if this is y, this is c. Now notice that if this is y and c, we get c equals to y squared, right? Which means it looks like this. Let me use red color. Which means it looks like this. Okay, and then the third one on XC plane, we have, same thing, huh? Which means C equals to X squared. So when we sketch the graph, if this is X and this is Z, it will still look like this. Now, try to arrange this into 3 dimensions such that if you see that from above, it looks like this. This is a view from above. View from above. Okay, this is the view to right wall. And this is the view from left of left wall. Now, if I try to put things together, then it seems like the ground shadow should be somewhere like this. That's the ground shadow, okay, on XY plane. Okay, yet the graph will look like, let me use maybe a black color and make it thicker. It will look like this. Let me help with a little shadow. Like when I do the little shadow, the shadowing, it's like, it looks like this. Okay. To which, if I try to do the shadowing to right wall, if I do the shadowing to right wall, it will look like this. Okay, where it actually looks like that. Okay. So this guy here, this guy here is this guy. Okay, the shadow of that space curve on YC plane. Okay, I think the bottom, the one that I did earlier, is better. The shadowing that I did earlier is better. The one to XY plane. Oops, I cannot erase that anymore. Yeah, the one to XY plane. So if I do it this way, yeah, you can see it better, right? But what they ask you to do is actually only this part here. Only this part. Okay. Kind of like imagine the following. I saw this illustration somewhere before. So what happened is, suppose I have a cylinder, just not a super long cylinder, it's just like this circular cylinder, okay, which if you project to the ground, it looks like, if you project that to the ground, it looks like a rectangle. When you project that to the right wall, it will also be a rectangle. Okay, but when you project it to the left wall, it is a circle. So imagine if you see the ground, you look at the ground, it looks like a rectangle. You look at the right wall, it's rectangle. But when you look at the left wall, it is actually a circle. Then can you reimagine what that solid, original solid, look like from the shadow? Okay. Yeah. In other words, you have three different perspectives. You see that from above, you see that from the left to the right wall, and then from right to the left wall. Okay. Using those three perspectives, can you imagine what the figure actually look like? Okay, that's for number 16. Let me just go on to the next one. The next one here is actually more fun, but I will also at the same time teach you a new technique, another technique, which you actually learn in Calculus 2, supposedly, and in trigonometry, on how to sketch the graph of, parametric equation, or in this case, a space vector function. Okay, a higher dimension. Now I'll give you idea first. I will erase this later on, but think about this. Suppose I have in 2 dimension parametric equation x equals to sine t, y equals to cosine t. Okay, the way we look at this, this is x squared plus y squared equals to sine squared plus cosine squared, which is equals to 1, right? So the outcome will be a circle, a unit circle. Okay, now does it mean that the curve of this parametric equation give us a circle? The answer is not necessarily. It depends on how the t moves. Let's say if the t moves from 0 to 2 pi, then it will give us a full circle, one round, right? But if I only have from 0 to pi, for example, then it is only the upper, actually no, not the upper one. It will give us the right semicircle, right? In fact, it will move in this direction, starting from here, t equals to 0, to here, this is t equals to pi. Okay, now my point is this. When you put them together and make it into a rectangular equation, okay, the rectangular equation gives you the red circle, right? But the curve may be only part of that, not the whole path, not the whole red circle. Okay, another illustration. Suppose I have x equals to cosine t and y equals to cosine t. This one is easy, supposedly, right? Supposedly, you say, well, x equals to y. But if you think about it, x equals to y is actually a diagonal line with slope 1. Okay, that's the equation of x equals to y. However, if we consider these only, then notice that cosine t has the range between -1 to 1. In other words, when you graph this, you will only get actually a segment, not the full line. It's only a line segment because the range of the cosine t actually from -1 to 1. Okay, so the x will be from -1 to 1 only, the y also -1 to 1. In other words, even though I make them into xy rectangular coordinate equation, okay, the actual curve may be only part of that original bigger graph, not the full one, not the full one. Okay, that's the technique. That's the technique. Now, so if we try to use that idea into this 3-dimension using the concepts of putting them together and make them into rectangular equations, then we will only get we will get the surface maybe that in which the curve actually traveling. Okay, so for example, number 21, we have the space curve managed by t cosine t, y equals to t, t cosine t for the x component, and then the y component is t, and then the c component is t sine t, where t is non-negative. Now notice that the x component and the y component, x component squared plus z component squared, will give us t squared cosine squared t plus t squared sine squared t, which is t squared, which is y squared. Right? Now, because t is positive, therefore, because t is positive, then you will see the y will also be positive. Okay, but if you notice what is this, you can think of this as r squared equals to y squared, r equals to y. Okay, if we have yr coordinate, then that's what it looks like. Right now, you spin it. Okay, it gives you a cone that opens to the positive y direction, right? Okay, now, so RT, the space curve RT, must be part of this cone. Okay. Now, when you look at the graphs here, which of those actually give you the curve that travels on this cone? You can see it will travel this way maybe, right? And that mimics the second one, right? This is mimic for number 21. Does it make sense? Okay. Let's go on. Number 22. Number 22, we have RT is cosine t, sine t, and 1 over 1 plus t squared. Now you can see x squared plus y squared equals to 1, right? Okay, in other words, the curve RT must travel on the surface of r equals to 1, like in polar. Okay, and in fact we can say more. That the c component, if you see the ht, the c component, 1 over 1 plus t squared, has the range positive range. Actually positive range, but at the same time is less than 1, huh? Is it right? Cannot be negative. Yeah, it cannot be negative. Right? As t goes to very, very large number, right? Then the curve becomes near to 0, right? Okay. What happened when t equals to 0? When t equals to 0, so r0 will be r, but this is less than equals to 1. R0 will be, the coordinate will be 1, 0, 1, right? Okay, as if we are saying that if we have that, it will be 1, 0, and so on. That's the starting point. In fact, that will be the highest point. That will be the highest point. Okay, it will be on a cylinder parallel to z-axis with axis z-axis. Okay, so it will be either this one here or this one here, right? If you think about it. Okay, but the thing is, in graph number 4, it seems like, hold on, when graph number 4 when t equals to 0, yeah, it seems like this is the maximum, right? This is the maximum, which is not 101, and this guy here, maybe it makes more sense, right? It makes more sense. This is the maximum. So I will say the graph should look like this. That should be, the graph will be graph number 6. Okay, and this is for equation number 22. Okay, now how about number 23? Let me do it here, so it's everywhere. Number 23, we have RT equals to t 1 over 1 plus t squared and t squared. I think I want to see this from to the left wall because the x squared equals to z, right? So on the left wall, it should look like this. Okay, this is the left wall. Left, maybe I should say xc plane projection. Xc plane, that's what it looks like, right? Now, so from all these pictures here, I think the one that makes sense that looks like that is graph number 5. Okay, now we can also see that if we try to do the YC projection, YC plane projection, then you will see the Y is equals to 1 over 1 plus Z. Is it right? Okay. But the C is at least 0. If I try to graph this, when the Z is 0, the Y is 1. If this is Y and this is C, okay. But as C increases, the Y becomes, as C increases, the Y becomes very small. So it looks like this. Yeah. So I think if you project this on the YC plane, it will give us this shadow here, which mimic what we have there. Okay. And if we project this on XC plane, it will give us the parabola that we want. Right? Can you imagine this? Okay. So yes, this will be graph number 5. This will be graph number 5. And this is for equation number 23. Okay, let's go on. Number 24. Number 24, what's the equation? Cosine t, sine t, cosine 2t. So RT is cosine t, sine t, cosine 2t. Oh, seems like x squared plus y squared equals to 1. But at the same time, the c, which is cosine 2t, is cosine squared t minus sine squared t, which is x squared minus y squared. So it is part of that, what they call that again? Hyperbolic, elliptic parabolic, parabolic, hyperboloid. I forgot the name. The one that looks like this. The one that looks like this. The one looks like that. Okay, but at the same time, it is intersected by a cylinder with a z-axis. Let me use different color. Okay, so the path must be traveling like this. Okay, and I think the one that matched that one is number 1, right? So this is number 24, and this is the first graph. Okay, let me jump to number 26. Number 26, we have cosine squared t RT is cosine squared t sine squared t and then t. Okay. Seems like from here we see x plus y equals to 1, huh? So it must be on this plane. It must be on the plane that give us 45 degrees. And notice that the x and y has to be at least 0, right? Because the range of cosine squared, the range of sine squared, right? Okay. xy has to be at least 0. And then the c will increases from there. Okay, so it will be yeah, and then this is at most radical too. Yeah, it is always equals to 1. And then so it must be on this plane. It must be on this plane here. Oops. It must be on this 45-degree plane, right? With theta equals to 45 degrees. Okay, and when the t equals to 0, then the t, oh no, I'm sorry, I draw it wrong. No, that's not what the graph look like. My bad. No, x plus y equals to 1, not x equals to y. So it's supposed to be this one here. My bad, it's from here. In fact, it must be on this plane, right? Because x plus y equals to 1 on xy plane looks like that, right? Okay, and then when t equals to 0, there'll be 1 0 0, so it will be 1 0 0. This is the coordinate. And then when c is equals to pi over 2, there'll be 0 1 pi over 2. So it must be like moving this way, right? Okay, yeah, moving like that. Which one is that? Oh, that's number 3, huh? It's number 3. It's number 26. Okay, now you can see number 25, at least when you catch the x and y, notice that x squared plus y squared equals to 1, yet the c is increasing, right? In fact, it is increasing faster and faster. So by just thinking that way, oh, it must be on the cylinder with axis z-axis radius 1, and the curve actually going up faster and faster, right? Then it must be graph number 4, right? This is graph number 4, and this is for number 25. Okay, now don't forget you can use GeoGebra to help you graphing it, but I think our issue is not about can we use graphing software to graph it. I think the issue is like, can you look at the space curve, the factor function, and then imagine what the path look like? That's actually the challenge. Okay, now to graph that, again, you can use GeoGebra to confirm. What we do here is try to match from the factor function and try to guess which of these 6 graphs actually the one matched that the most. Okay, let's go on further. The one I do here, as I remember, I don't really cover that in class. Let's see number 40. Okay, so we have the vector function that is the curve intersection of two surfaces. So we have the first surface, let's call that surface 1, which is x squared plus y squared equals to 4. Now think of this, parameterize that in x and y. So I will say x equals to 2 cosine t, right? Y equals to 2 sine t. And then the second surface z is equal to xy. So using that, 2 cosine t, 2 sine t, this will be 2 sine 2t. Okay, so the parameterization RT, the space curve may be parameterized with 2 cosine t, 2 sine t. Notice that it must be on the cylinder, right? Okay, and it is also on the surface C equals to xy. Okay, don't forget, 2 sine t cosine t is sine 2t, but that's something I do expect you to already memorize though. Okay, number 42. On the paraboloid, so the first surface is z equals to 4x squared plus y squared, and the parabolic cylinder, y equals to x squared. Now notice that the y depends on x. From x you can get y, and together x and y you can get z. Can you see that pattern? Okay, so let's use x as our parameter. Okay, so you set x equals to t, so the y will be t squared, and the c will be 4t squared plus t squared being squared, which is 4t squared plus t to the fourth. In other words, now we can parameterize that rt by t squared 4t squared plus t to the fourth. Okay, let's try to sketch this though. Let's try to sketch this. So basically, it looks like a parabolic. Right? So looks like this, maybe. That's for S1. Okay, and our S2, y equals to x squared, looks like this on the ground, but then you do that. Okay, now then the intersection will look like this. You think so? Right, it has to be on the paraboloid, but also has to be on the cylinder. Okay, so as t goes from negative infinity, it must be something very high up there, and then it goes down, it touches the origin, and then it will go up again. Okay, now you can use the GeoGebra to graph that. Let's try to do that. Where's my GeoGebra? Okay, so we have z equals to 4x squared plus y squared. You are seeing my curve here, right? And then the second one is y equals to x squared. The thing is, oh, I need to make it 3D. Sorry. So c equals to 4x squared plus y squared. Okay. And then y equals to x squared. Let me change the color for one of them. And then let's turn this a little bit. Now, can you see that intersection already? You see that intersection? Maybe I screenshot this and then put it on our graph, on our node. Make it a bit smaller. Right, and then the curve start from here. You see this is the intersection of the paraboloid and the cylinder, and then it goes down here, and then it goes up here. Oops, no, I want that to be curved. And later on it goes up here. Okay. That's for number 42. Let's see number 44. Move this down. This is semi-ellipsoid. Why? Because we want the y to be positive. So it is an ellipsoid, but it opens to the right. And you have the cylinder x squared plus c squared equals to 1. Let's deal with the cylinder first. Okay, so our S1 will be x squared plus c squared equals to 1. Because then it gives us x equals to cosine t, and then the z equals to sine t, right? You see what I mean? Okay, now then for S2 we will get x squared plus y squared plus 4c squared equals to 4. Now let's solve for y here. Y equals to 4 minus x squared minus 4c squared. In other words, y equals, supposed to be plus minus, but we know that the y has to be positive, right? Y has to be non-negative. So y is square root of 4 minus x squared minus 4c squared. Okay, now therefore we will say RT is equal to cosine t square root of 4 minus cosine t dx, cosine squared t minus 4 c squared, which is 4 sine squared t, and then sine t. I think I can simplify the y component a bit. Let's do that. Well, because this guy and one of the sine squared give you another one, right? So this is 3 minus 3 minus 3 sine squared t. Am I right? But that still gives us something though. Oh, I didn't know that we can go that far, but let's see. So this will give us square root of 3 of, is it cosine t? But it is in absolute form. Okay. Last one, I think number 48 is the last question. Two particles travel along space curve. Now notice that both of them here happen to use the same t. So the t for this guy is the same t for this guy. Okay. Now the question is, do they collide? Now to show that they collide, they need to be at the same coordinate at the same time. In other words, to collide, your R1 t equals to R2 t. Okay, so let's fix them. So the x component, t equals to 1 plus 2t. The y component, t squared equals to 1 plus 6t. And the c component, t cubed equals to 1 plus 14t. But if we see here, when we solve that, you will see t equals to -1. But then when t equals to -1, we end up with 1 equals to 1 minus 6, which is 1 equals to -5, is a contradiction, right? In other words, from x component, they're supposed to collide when t equals to -1, but when we use that on the y component, t equals to -1 does not give us the same y's. Okay, so R1t intersect, don't collide, and R2t don't collide. Means they never reach the same coordinate at the same time. Now, do they intersect? Then R1t needs to be equals to R2s. Okay, intersect means the path intersect, but they may not reach the same the intersecting point at the same time. Okay, they don't reach the intersecting point at the same time. Okay, so if I try to solve that, t equals to 1 plus 2s and t squared equals to 1 plus 6s, t cubed equals to 1 plus 14 s. Now we will use the first two equations to solve for t and s, and we will try that on the third equation to see if it is consistent. Okay, let's do so. So from equation number 1 going to equation number 2. Equation number 1 goes to equation number 2. We will get 1 plus 2s squared equals to 1 plus 6s. So 1 plus 4s plus 4s squared equals to 1 plus 6s. So I get 4s squared minus 2s equals to 0. So s equals to 0, or s equals to 1. No, I'm sorry. Let me factor that first. This is 2s, that's 2s minus 1. S equals to 0, or s equals to 1/2. Now when s equals to 0, the t is 1. When s equals to 1/2, the t is 2. Now we try that check on number 3, equation number 3. Okay, when using t equals to 1 and s equals to 0, 1 cubed, is it equals to 1 plus 14 times 0? And you will see 1 equals to 1. That's true. So using that, we see that the path collides at R11, which is R20. Okay, and you will see that is the coordinate will be 111, huh? Right? Okay. Now, how about when s equals to 1/2 and t equals to 2? So when t equals to 2 and s equals to 1/2, do they collide? The first t cubed equals to 1 plus 14 times 1/2. So this 8 equals to 1 plus 7, that's 8 equals to 8. Oh, wow, okay, that's also true. So R1 at time T2 equals to R2 at S equals to 1/2. Okay, which is, let's see, that would be 2, 4, 8 at 2, 4, 8. Okay, in other words, the paths intersect at coordinate 1, 1, 1 and 2, 4, 8. Okay, now that's for this 13.1. Now don't forget that you can use GeoGebra to sketch the graph. Okay.